All right, so we are in now week number 12. And as I mentioned last time, this week is a non-lecture week where people can just ask questions and I will answer them, and no attendance is taken, although I love the fact that you guys are all here. I'm going to share my screen because we have our first question, and that was on homework number 20, you said?
Yeah, number 7.
And number 7. Okay, so this one right here. Okay, it says, so this is 2027. It says the Trial Urban District Assessment, TUDA, is a government-sponsored study of student achievement in large urban school districts. TUDA gives a mathematical test score from 0 to 500. A score of 262 is a basic mathematics level, and a score of 299 is proficient. Scores for a random sample of 1,100 eighth graders in Dallas at X bar equals 271 with standard error 1.3. A, we don't have the 1,100 individual scores, but use of the T procedures is surely safe. Why? So remember, the T procedure is a robust procedure, and when the sample size is larger, it overcomes issues that we might have, like non-normality and things of that nature. So because the sample size is very large, 1,100, certainly large enough that we don't have to worry about any issues like skewness or outliers. It's not always safe, right? It has to be a certain size. What if it's skewed? What if there's outliers? But we know by the concept of robustness that if the sample size is large enough, it can overcome all those difficulties. So that part A is just the sample size is very large. Does that make sense?
Yeah, that's what I initially put. It was like part B and C that were confusing for me.
Okay, so let's compute a 99% confidence interval for the mean score of all Dallas 8th graders. So the 99% confidence interval is going to be X bar plus or minus T star times S over the square root of N, correct?
Can you repeat that formula one more time just so I can write it down?
Well, hopefully you already have it down, but it's X bar plus or minus T star S over the square root of N.
Okay, yeah.
Now, in our case, X bar is 271. We need T star for a 99% confidence interval. Let's see what table C gives us. T distribution critical values. So let's find T. Of course, the calculator can do it even better, but here we go. We have 99% confidence for, what was the sample size again? 1,011 or something? 1,100. So
1100, yeah.
means 1099 degrees of freedom. So there's no 1099, but once you reach 1,000, I mean, basically you go to the lower one because higher up is always less precise, and we'd rather go less precise than more precise. So for a 99% confidence level, which is this column here, I'm going to use 2.581. Okay, and then we have S over the square root of N, but they didn't give me S. They gave me the standard error. The standard error is already including the S over the square root of N. It's the whole thing. So just times 1.3. So I have 271, then 2.581, whoops, 2.581 times 1.3. So it's 271 plus 3.553 or minus 3.553. When I subtract, I get 267.6. And when I add, I get 274.4. So the confidence interval is from 276.6 to whatever I just said. I don't even remember my numbers.
So it's just the two numbers that surround that in between, right?
I'm sorry, say again.
So it's the two numbers that are on either side of that number you just computed, right?
Well, the interval is from this number to this number, right?
Right, yeah.
So there's two ways of saying that. You can either give me the left and the right edge, or you can give me the middle plus or minus the margin of error. That tells me how to get to the left and right edge.
Okay.
So the formula is middle plus or minus the margin of error. And if you subtract and add, that gives you the two edges.
Okay, got it.
Right? And then part C. Urban children often perform below the basic level. Is there good evidence that the mean for all Dallas 8th graders is less than the basic level? Well, our sample size is 271, correct?
Right.
Sorry,
No,
not our sample
the
size.
sample size is 1100.
I'm sorry, the sample size is 1100. The sample mean is 271, correct? Where 262 was basic. Well, the entire confidence interval is above 262, right? The entire confidence interval is above 262. So we are 99% confident that the mean for all Dallas 8th graders is between 267.6 and 274.4, all of which is higher than 262, right? So is there good evidence that the mean is less than the basic level? No, the basic level of 262 is not in the interval. The entire interval is above it, right?
Right.
There's no evidence whatsoever that the mean is less than 262. If our interval overlapped and part of it was below, then there would be evidence. But in this case, there's not. The entire thing is above 262. Does that make sense?
Yeah, so for B, that's the one I was mostly confused on. You would just plug that number into the formula and you'll get those two edges on both sides, right?
Yep.
Okay. Thank you.
You're welcome. So, any other questions?
Yes, Professor, I have one.
Okay, which section?
Same chapter, but this time question 8.
Same chapter, but this time question 8.
I was just I was confused on the like matched pairs design.
Okay, well, let's take a look. Our bodies have a natural electric field that is known to help wounds heal. So just changing the field strength, slow healing. A series of experiments with newts investigated this question. In one experiment, the two hind limbs of 12 newts were assigned at random to either experimental or control groups. This is a matched pairs. Okay, the reason why it's a matched pairs design is because each of the newts had one leg in the control group and one leg in the experimental group. It wasn't just 12 control and 12 experimental, because all newts are different. Maybe some newts are better at healing than others. But by using the same newts for both things, we can more accurately determine whether or not there's a difference between the value we get with the electric field change, the experimental group, or leaving it alone, the control group. Does that make sense why it's matched pairs? Because we're matching them. Left leg, right leg of the same newt. Yes, no?
Sorry, I remuted my mic. Yes, that makes sense.
Okay.
And then go ahead.
Yeah, so I'm just reading. The electric field in the experimental limbs was reduced to 0 by applying a voltage. In other words, we removed the electric field completely. So the very first sentence said, electric fields are known to help wounds heal. And then what we did is we removed them. So the control limbs were left alone. And the experimental limb was by removing the electric field, which should make healing more challenging. And the table gives the rates at which new cells closed a razor cut in each limb in micrometers per hour. So the control limb should be better because the electric field is there, and therefore it should heal faster. And therefore more micrometers should be healed per hour versus the experimental limb, which had no electric field, and therefore was worse. Okay, so do we understand at least what's going on here, which is always
Yeah.
the first step?
Yes.
Okay, so why is this a matched pairs design? So it's a matched, let's look at the wrong ones first. The bottom one says it's a matched pairs design because the control and experimental limbs are matched by newt because there were two different treatment options for each newt. Well, actually, that's true. So let's see if there's another answer that's better. It's the matched pair design because each newt has two hind limbs that can be compared. Well, that's true as well. There's a matched pairs design because the control and experimental groups are matched by newt because a newt's ability to heal on one leg is independent of the ability to heal on the other leg. Well, this is not tricked. Why would they be independent? They're actually, you know, if a person or an animal is more likely to heal in one leg than the average, they're probably more likely to heal in the other one. So this one is out. Because it's a matched pair design because the control and the experimental groups are matched by a newt because a newt's ability to heal in one leg is not independent of the ability to heal in the other leg. So that's true. So really there's three of them that's true. I guess it's just the most descriptive of what's going on. I guess that's the reason. Yeah, I guess it combines everything, right? We're comparing them. There's two different treatments, but there's not an independent. If they were independent, it would just be two different groups. Because they're not independent, that means there's a connection, which is why we're matching them up. So I guess it's that extra word, not independent, or two words, that is really the key for why the first one is correct and more correct than the third and the fourth. Hope that makes sense. So then it says, choose the correct stem plot of the differences between the limbs of the same newt. Control minus experimental. Control minus, so that's 8, 10, 12, 9, and so on. Right? So here's 8. Here's 10. Here's 12, and so on. Hopefully that wasn't the question that you had. Or is the question been answered, or is it not there yet?
That is the same question. Like, oh, never mind. I misunderstood what you just asked. Okay.
So have I answered the question or not yet?
Yes, you did.
Okay, so we can move on to another question if someone has one.
Yeah.
Okay. Well, I am here to answer them if people have them.
Professor,
Yes.
actually for that same question,
Yeah.
could you run through how to do the p-value? Because I'm able to get the test statistic, but just getting the p-value has always been confusing.
Okay. Do you want me to do it by hand or by crunch it? Because
If possible, both. I don't know.
sure, I can do that.
Because
Okay.
crunch it like is best because it's easiest, but by hand just in case.
Right. Well, crunch it gives us the answer. It doesn't explain where the answer came from.
Yeah.
Okay. So mu is the mean difference between the control and the experimental group and healing rates. What are the null and alternative hypotheses? So what are we testing? We're trying to determine whether or not the healing goes down when you remove the electric fields, which would make control minus experimental positive. So the null hypothesis is that there's no difference. Mu d, the mean, or mu is equal to 0. And the alternative is that mu is greater than 0, that the control is higher than the experimental. All right, so that's part of that one. Carry out a t-test. Okay, so let's go back up here and let's load up crunch it. Okay, so crunch it says let's carry out a t-test. We go to statistics, we go to t, it's a matched pair. The first variable is going to be the control. Second variable is the experimental, control minus experimental. We're looking for hypothesis test. The mean is 0. We're checking to see if it's greater. And we get a t statistic of 2.076 with a p-value of 0.03106, correct? Right, that's what it says there, right?
Yep.
So the question is, how do they get the p-value? Well, let's load up, not load up, but let's consider the situation. We got a bell curve. The null hypothesis is claiming that the mean is 0. So the center of our bell curve is 0. And we got a value of 2.076, which is somewhere off to the right, 2 deviations plus a little bit more off to the right, correct?
Because 0 is the center, and then
0 is the center, and,
2 would be off to the right, yeah.
and we are 2.076 deviations to the right. And the p-value says, what's the probability of being more extreme than our value? So more extreme than our value in a one-sided case means we're looking for the probability of landing in that shaded region. In other words, we're looking for the probability of being past 2.076. Essentially what we want is we want the area here. That area, according to them, is equal to 0.03106. How do we get that? Well, let's go back to here, the t-table. So we know based upon our question or on Crunch It, there's 12 data points, which means the degrees of freedom is 11. So I go to row 11 and I'm looking for my value of 2.076. So 2.076 lies somewhere between these two numbers. Do you agree?
Yes.
Okay, which means that the shaded area is somewhere between 5% and 10%, because remember, the area in the middle is your C. So if we have 95% confidence, if there's 95% area in the middle, our value will be 2.201. If it was 90% in the middle, our value would be 1.796. So we are somewhere between 5% and 10% being outside, which is somewhere between 2.5% and 5% being on this just one side. So our p-value based upon this table, which is not extremely accurate, is somewhere between 2.5% and 5%. Crunch It gives me a much more precise answer. But based upon this table, I can't really do any better than that. If I wanted to do better, what I can do is I can take out my calculator. And what I can do is I can go to my t-distribution. It starts with z, but if you go down to 4 and yeah, if you go to 4, it becomes t, inverse t. So I go to 4. But that's inverse. So how do I get the actual t on? I go to 6 t CDF, not z CDF, but t CDF, and I still am on the right place. So my calculator's a little screwed up. So TC, there we go. So we go from a lower value of -infinity. Actually, we go from a lower value of 2.076 to an upper value of really up with a freedom of 11. So here are my parameters. My lower is 2.076, which is my t statistic. I go up to basically infinity, a huge number with degrees of freedom 11. I hit enter, and it gives me my probability of 0.031062976. Does that match their p-value that they give me? 0.03106, pretty close. Actually, it's almost identical. Does that make sense? Wasn't that fun?
I was wondering for the t-statistic table, when would we use the portion at the bottom? Not the z star, but the 1 and 2-sided.
Well, if we know that it's a one-sided test, which we do in this case, and I wanted, for example, if I said your alpha is, let's say, 5%. So that means if your alpha is 5%, that means we want a 5% chance of landing to the right of that value, right? We want the shaded region to be 5% on a one-sided test, which makes the shaded regions on the outside together, right and left 10%, which makes the center area 90%, right? So if I have a 5% area to the right, that means the center area is going to be 90%. So I go to 90%, and what I can do is I can go all the way down here, and you see how that corresponds to a p-value of 5%?
Oh, that would just be the determining the p-value if
Exactly.
you were given alpha.
Exactly.
And then for Z star, if
So Z star is just, this is the t-table.
Mhm.
As the number of degrees of freedoms goes up, you can see that these values get smaller across the board. In any column, they get smaller.
Mhm.
And as you get really to lots and lots of degrees of freedom, we reach this row. So a T star just becomes a Z star if the sample size is large enough,
That makes sense.
right? So that's all it's claiming, is if the sample size is big enough, T star essentially merges into Z star. It gives you the Z star values, it gives you the P values for given levels of confidence, and it gives you degrees of freedom. Lots of information here. But unfortunately, if you land at a number in between like we did, then you have to guesstimate. Or use a calculator, which gets the exact value. Make sense?
It does. Thank you.
You are welcome. All right, well, that's just my, okay, let's stop sharing now. Hopefully I didn't have anything embarrassing in my emails, but I didn't. Yes, I don't think I did. This is really exciting, everyone. I'm going to stop recording, pause recording in between questions, so that people who are watching this video later don't have to wait through lots and lots of silence. Recording again. So, okay, which question is this?
Chapter 20, question 8.
Chapter 20, question 8. Okay, let me find chapter 20, question 8. So first I'm going to remove crunch it here. And I'm going to remove this, and I'm going to close that. And I'm going to go back to here. And do question 20, number 8. Isn't that the one we just did?
Yes, but I realized, I think I know why I keep getting it wrong, but I'm not sure.
Okay. Why do you keep it wrong?
So near the bottom of the question,
Yeah.
it says carry out a test that omits the outlier.
Okay. Well, in that case, what you have to do is first you got to ascertain what is the outlier. So let's go back to crunch it. And let's look at our values of control minus experimental. 8, 10, 12, 9, 11, 1, -6, 31, 5, -13, 2, and 7. So which of those is the outlier, what do you say?
31.
So let's remove that one. Let's just 56 and 25. Let's just get rid of it.
Okay. I wasn't sure if you had to delete both of them or not.
Well, yeah, probably, because it's because to match up, they have to be the same thing.
Right. Okay. That logically
If
makes
we
sense.
do this, we get that. So what does that tell us?
Okay. So it's 0.179. And then
What's 0.179? I'm sorry, what's 0.179? I don't see 0.179 anywhere.
the t statistic, it's
1.788, it looks like. No?
right, but in sapling it's rounded up for the answer option.
Here it is, I found it. Okay, yes, sorry. Okay, go ahead. Okay. I see, as your choices, you mean?
Yeah.
Oh, I see. So let's take a look. So here it's 1.788 becomes 1.79 with a p-value. It's a little more than 0.05. Yeah, so that one is correct.
Yeah. Okay. All right. Thank you, Professor.
You're welcome. I'm going to stop sharing again and pause it until someone has a question. All right, so we're back. So someone asked about question 1 on chapter 22. So let me load up. Let me first start sharing again. And that is question 1 on chapter 22. So let me first figure out how to get out of here. Oh, okay. 22. Question number 1. Canada has much stronger gun control laws than the United States, and Canadians support gun control more strongly than New Americans. A sample survey asked a random sample of 1,505 adult Canadians to agree or disagree that all firearms should be registered. Of the 1,505 people in the sample, 1,288 answered either agree strongly or agree somewhat. A, the survey dialed residential telephone numbers at random in all 10 Canadian provinces, omitting the sparsely populated northern territories. Based on what you know about sample surveys, which are likely to be the weaknesses in this survey? Well, obviously they exclude all the people who don't have phones, and they exclude all the people in the northern territories, correct?
My number 1 for chapter completely different than this one.
Is it?
Yeah, it's not even like talking about the same kind of problem.
For question chapter 22, you said?
Yes.
What's the title for it? Can you read me the first couple questions?
A radio talk show host is interested in the proportion P.
Hold on. I don't have a radio talk show host here. Do you know the labeling for the question? Like rather than just question 1, is it 22 point something?
It doesn't show that for me.
Why don't you share your screen?
One second.
Okay, I'm gonna allow anyone to share. Go ahead and share your screen so I can see it. Well, this says section 21. You said chapter 22.
Wait, I don't know why it's, wait, hold on.
Oh, no, it still says section 21.
Okay, I don't know what was wrong with that. Never mind. But anyway, can you help me go over this one?
Hey, which one? The one I was doing?
Yeah.
So the Canadian one.
Yeah.
Okay.
I don't know why it was. I guess I have to refresh it.
Okay. Well, so obviously, oh, someone texted something. Let me just see what they said first. He's asking, oh, for the practice quiz 22.
Yeah, I was confused. Like, I don't know why it was showing the practice quiz instead of the actual homework.
So, but which one do you want? For clarification, you want the practice quiz, correct?
Actually, I would like the homework. I apologize.
Okay, so you do want the homework. All right. Okay, so this is the question, right?
Great.
So obviously, just right off the bat, if they're calling people with phones, then anyone without a phone is not going to be called, right?
Right.
We're only calling people who in the 10 Canadian provinces, they omitted the Northern Territory. So anyone in the Northern Territory is not going to be included as well, right? So obviously the last one is certainly going to be one of the ones that's a problem.
Right.
Okay. People are protective of their privacy and therefore may give insincere answers. Well, that's always the case. I mean, you always have that no matter what kind of survey it is or what kind of, I mean, that's true, but I don't think in this case, I don't really see that as being a weakness in the survey itself because so many people answer in both directions. I don't really see that one. Canadian citizens who live in other countries, no. Well, that's true. It does exclude Canadian citizens who live in other countries, unless, of course, they have a phone number in Canada. But why is that a weakness? because the people who live in other countries are probably, I would say people who live in other countries are probably just representative of the average Canadian anyway. I mean, you have people all over the place who would live in other countries. So I really don't see that as being a weakness either.
All right.
However, people don't like answering the phone that they don't recognize. So there's certainly going to be a high non-response. Okay, that's certainly something that we expect to be true because, you know, I mean, how often would you enter the phone for a survey? I know I never would. So even as a statistician, I don't want to be bothered.
Right.
So nonetheless, it says nonetheless, act if we have an SRS from adults in the Canadian provinces. Suppose it's an SRS. Give a 95% confidence interval for the proportion who support registration of all firearms. Okay, well, what's the formula for the confidence interval?
Isn't this going to be I believe this is going to be a one sample
It's one sample.
t-statistic kind of program for country.
Okay. Oh, you want to go to Crunch It and do it. All right, we can have Crunch It do it. How do I? Oh, I can't do Crunch It. So we got to do it by hands. So what's the formula?
Exactly. I can't really remember that well. So
You can't remember. It is p hat plus or minus z star square root of p hat 1 minus p hat all over n.
one second. All right.
So now we've got to plug it in. What's my p hat going to be?
P hat is going to be 1505.
No.
Wait,
1,505 is the number of people in the sample.
right, that would be the end then.
That's going to be the n. So what's the p hat going to be?
The P hat is going to be can that just be 1288?
No, 1,288 is the number of people who answered yes or strongly, the number of successes.
Not sure.
P hat is the proportion of successes. It's the number of successes divided by the number of trials.
Okay, so
So what is it again?
sorry, I'm just
Yeah, write it down. It's okay.
I'm not really sure. I'm just having a lot of trouble.
For which one?
Trying to input the stuff for the into the equation.
Well, what's the formula for p hat?
P hat plus or minus c.
No. What's the formula for p hat? What I'm saying, how do you calculate p hat?
I can't remember.
Okay, so p hat is the number of successes divided by the number of trials. How many successes were there?
1288.
1288. How many trials were there?
1505.
1505. So p hat is just 1288 over 1505, whatever number that is.
.8558.
I believe you. 1288 divided by 1505. So that's my p hat. Then we got to multiply that by 1 minus p hat. Then we have to divide that by n. Then we have to take the square root of that. So what do we get when we do that?
It went a little bit fast for me, but I can.
I'm sorry, I
Right.
apologize. I apologize. I can slow down.
I did 1288 over 1505, which gave me 0.85581.
0.88. Yes, that's going to be our p hat.
Right.
So now we got to plug p hat in. Well, we first need z hat. Sorry, z star. Right?
Right.
We need z star, but we still have p hat. We have 1 minus p hat. We have n. We have everything else we need. All that we're missing now is z star. So how do I find z star?
I'm sorry, I can't remember.
That's okay. So you have to look at the confidence level. What's the confidence level here?
95.
95%. So anytime we have a 95% confidence level, Z star is automatic. What number do you recall? Maybe you wrote it down somewhere. Maybe someone else in the class can answer. What number is automatically the Z star whenever 95% confidence level?
I remember writing it down. 1 second. I believe it was 1.96.
It is 1.96. Excellent. So let's put everything in together then. So what do you got?
1 second. Sorry. For some reason I got 0.177.
That's not, what do you mean for some reason? That's the right part for that part.
I don't know, I'm saying for that specific part.
Yeah, that's correct. When you do 1.96 times the square root of p hat, 1 minus p hat over n, you should get 0.0177.
Right.
So now you have p hat plus or minus that.
Okay, 1 second.
Okay.
So for then I did 0.8558139.535 plus the number we just got, and then it gave me 8.8735599652.
Excellent. That's the right edge of my confidence interval. And now what's the left edge of my confidence interval?
0.838067948.
And you are done.
All right, thank you, Professor.
You're quite welcome. All right, so I'm going to stop sharing again. And we have another question. Which one would you like to ask?
21-2.
21, chapter 12. Oops, that's not what I'm doing. So I'm going to share my screen. And we are now going to chapter 21. Question 2, you said?
Correct.
Okay. Oh, I see. Section 21 must be my section. That's not chapter 21. Okay. 21, question 2. Okay. This is the one, correct?
Yes.
Do women and men differ in how they perceive their life expectancy? A researcher asked a sample of men and women to indicate their life expectancy. This was compared with values from actuarial tables, and the relative percent difference was computed. Perceived life expectancy minus life expectancy from actuarial tables was divided by life expectancy from actuarial tables and converted to a percent. The relative percent differences for all men and women over the age of 70 in the sample are given. Okay, so all that nonsense. Here are the values, right? We have these values for men and we have the values for women.
Right.
And what do we want to do here? Oh, we don't have to do it. They did it for us already. Let's take a look what we have. The null hypothesis is claiming that the difference of the means is 0, that there's no difference. And the alternative hypothesis that the difference of the means is not 0. So this is a two-sided test.
Mhm.
Okay. And in fact, it even tells us a two-sample t-test. It gives us the individual standard deviations, males and females, the individual sample means, males and females, the number in each data set, 1, 2, 3, 4, 5, 6, 1 through 7, the degrees of freedom by the calculator method, the difference of means, the t-statistic, the p-value. So the question is, do men and women over 70-year-old differ in their perception of life expectancy? Well, the p-value is a little more than 5%, which means that at the 5% level, we're going to reject the null hypothesis. Sorry, we would not reject the null hypothesis because it's more than 5%. But at the 10% level, we would reject the null hypothesis because it's less than 10%, right?
Mhm.
So there's somewhat strong evidence that men and women differ. We would reject at 10%, but not at 5%. In this study, by what percent did men underestimate their average life expectancy? And by what percent did women underestimate their average life expectancy? Well, isn't that what these numbers representing? I mean, I kind of got lost in all this math here. Let's just see if those are the answers. Yeah, there we go. I guess the fact that it's not a negative means they underestimated by 19.5%. The negative is telling us that it was an underestimation.
I see what that means.
As
Okay.
opposed to having the negative in there.
Yeah, I see. Okay.
Okay.
Yeah, because I was putting in negative, but I was like, that doesn't make sense. But
Yeah, so the negative, I mean, yeah, the negative is telling us that it's an underestimation, but I guess when they ask how much was it underestimated, you don't also include the negative, and it's kind of like being redundant.
mhm.
That make sense?
Yes.
Okay, I'm going to start pausing again. Okay, so we have a question. We're back, and someone is asking about which one was this again?
Chapter 18, number 4.
Chapter 18, number 4. So let me share this. We're going to chapter 18, question 4. And is that this one here, just to confirm?
Yes.
All right, so sulfur compounds cause off odors in wine. So winemakers want to know the odor threshold, the lowest concentration of a compound that the human nose can detect. The odor threshold for dimethyl sulfide is trained wine testers is about 25 micrograms per liter of wine. The untrained noses of consumers may be less sensitive, however. So how sensitive are the untrained noses of students? You want to estimate the mean DMS odor threshold among all students, and you will be satisfied to estimate the mean within plus or minus 0.25. So the margin of error is 0.25. We have 95% confidence, which means our Z star is how much?
Sorry, I was muted.
No problem. What's our Z star?
I have it written down right here. One sec. It's for a 95. Oh, mine says 99. For a 95, it's 1.96.
1.96. And sigma is equal to 9. So we have a formula, right? We know the margin of error is Z star sigma over the square root of n. That's a formula that we have. So if I want to solve for n, I get Z star sigma over m all squared, right? So my formula for n, which we have somewhere in the book, is Z star sigma over m all squared.
Okay. I'm about to answer.
So let's plug that in. Z star was 1.96. Sigma is 9 divided by my margin of error, which is 0.25. Square this number, and that gives me 4,978.7136. We always go up, so 4,979.
Okay, thank you.
You're welcome. So we are back. This is chapter 22, problem 2, you said?
Yes.
Okay, let me load up chapter 22, problem 2. Let me share my screen. Chapter 22, problem 2, you said, right?
Yes.
Okay, let's take a look at it. PTC is a substance that has a strong bitter taste for some people and is tasteless for others. The ability to taste PTC is inherited and depends on a single gene that codes for a taste receptor on the tongue. Interestingly, although the PTC molecule is not found in nature, the ability to taste it correlates strongly with the ability to taste other naturally occurring bitter substances, many of which are toxins. This is all very fascinating, but so far I have no information that I can actually use. About 75% of Italians can taste PTC. You want to estimate the proportion of Americans with at least one Italian grandparent who can taste PTC. Starting with the 75% estimate for Italians. So we have a starting point, 75% estimate for Italians. Okay, so we have this value that we can use as our starting point. So our P we're going to use is 0.75. How large a sample, so we're looking for N, we're looking for the sample size, must you collect in order to estimate the proportion of PTC teachers within plus or minus 0.11. So the margin of error is 0.11 with 95% confidence. So Z star is 1.96. So here's the information. I can assume P is 0.75. I'm looking for N. The margin of error is 0.11 and Z star is 1.96. You with me so far?
Yes.
So we know that the margin of error is going to be the square root of P, 1 minus P over N. Z star times
Star.
the square root of P1 minus P over N, right?
Yes.
So let's divide both sides by Z star and then square. So that gives us to that. Agreed?
Yes.
And then I'm going to solve for N. So I get N equals P 1 minus P times the ratio Z star over M squared. P1 minus P Z star over M quantity squared.
Okay.
So let's go ahead and do Z star, which we saw is 1.96 divided by 0.11, that quantity squared, multiplied by P, which is 0.75, multiplied by 1 minus P, which is 0.25. And that gives me 59.5, which goes up to 60. Hey, there it is, 60.
Oh, okay. So I was just, yeah. So we add the 1. That's where I got wrong. Because I got the answer that we just got, but I just forgot to do the.
No, you never, N it has to be a whole number because you're dealing with people.
Oh.
Right? So you have to go up to 60.
Okay. That makes sense.
Okay.
Okay, that makes sense. You can't have a decimal as a person. All right.
It's tough. It's tough.
I was,
I mean, if you're one of those who believes you can join the Jeffrey Dahmer fan club. But,
no. Okay, okay. And then for B, the estimated sample size required.
If you make no assumptions, then we have to take 0.5 for P.
Okay.
Because the value of 0.5 will give us the largest possible n, and we want to err on the side of caution. So if I do exactly the same thing as before, but this time instead of multiplying by 0.75 and 0.25, I multiply by 0.5 and 0.5. That gives me a higher number of 79.37, which goes up to 80.
Okay. And then
I
the
agree with
0.5 we would get from the two-sided P, right? Is that where we got the 0.5?
No, nothing to do with two-sided. If you
Okay.
have no information in advance about what P might be,
Mhm.
you take 0.5, because 0.5
Oh, okay.
will give us the largest n out of all possible values for P. And we want
Ooh,
the
okay.
largest possible n because we want to err on the side of caution and say, no matter what P actually is, we want to make sure that our sample size is large enough. And the largest sample size comes from a p-value of 0.5. Not a p-value, but a value of P of 0.5.
Okay, got it. Thank you so much.
You're welcome so little. Okay, I'm going to stop, pause. Okay, we have another question. Which one is this?
All right, it's a two-parter for my question. One is just understanding degrees of freedom as a
Okay.
concept. And that is going to be in regards to 21 question 4.
21 question 4. So hold on, let me load that up. 21 question 4.
And I'm looking at part C for that one.
Okay, so hold on, let me share my screen. Oh, I just had it. I just got rid of it. Why did I do that? Okay, 21 section 4. Part C, you said, huh?
Yep.
Okay, so we have a sample of 56. So 1 minus that is, sorry, that minus 1 is 55. And a sample of 27. So that minus 1 is 26. And the simple way out, according to this, option 2, we take the smaller of those two numbers. So we would take 26. So option 2, what degrees of freedom does option 2 use to get a conservative p-value for each study? So for the first study alone, of course, it's n minus 1, 55. And for the second study alone, it's 27 minus 1, which is 26. That's 19. Well, that's weird, isn't it? Is that your issue?
Well, because it's, let's see, if you scroll back up, it's separated into women and men.
Oh, I'm sorry. Thank you. I misread the question. So this is on option 2 used to get, oh, okay. Oh, I see. So for study 1, when they have the same sample size, we subtract 1 from each, we get 55 and 55. We take the smaller of those, which of course is just 55. For sample 2, when I have 27 and 20, I get 26 and 19, and the smaller of those is 19.
Mm-hmm.
Does that make sense?
Yeah, it makes sense, but just the concept of degrees of freedom.
Yeah. So yeah, at this level, degrees of freedom is conceptually very difficult to explain because it's really an advanced concept that you have to address at this level because the formulas depend upon it. Essentially, when we mean a degree of freedom, we essentially mean something that you have some independent control over. So if I say you have 10 numbers and their average is 100, and I say, what are those 10 numbers? You can make up the first 9 all you want, but the last one you have no freedom over. Once the first 9 numbers have been established, the last one comes along for the ride. We have no freedom. So there'll be 9 degrees of freedom for that situation. 9 numbers that are within your control, and the last one is kind of forced upon you. So in ways that are beyond the level of this course to understand, the idea of degrees of freedom is a sense that when I say there's 19 degrees of freedom, that means you have 19 values that you have control over, and everything else comes along for the ride.
Oh,
That's a very loose definition, but it's really the best we can do at this level.
can I say would it be proper to say it's kind of like Sudoku, where you have a number that's given, you have to kind of like add up or whatever, in that sense?
Yeah, in a sense, yeah.
Okay.
Yeah. But I mean, at this level, we're not going to really, ask you for explanations of degrees of freedom, merely how many degrees of freedom are there in a given situation. Okay.
Okay, and then you always subtract it from 1.
Well, the rule is you take the sample size minus 1, and that gives you the numbers that gives you how many degrees of freedom you have.
Okay.
And if it's 2 samples, then you do each one minus 1 and take the smaller of them.
Okay.
Now, the computer does it a different way, which is a lot more complicated, and so sometimes when the computer does it or a calculator does it, you'll get a different value than that. That's just because they're using the more accurate one. Excuse me. Sorry.
Thank you.
You're welcome. Okay, we
Hello.
have a question here, chapter 22, number 8 and 9. So I'm going to share my screen again. And we are going to do question 8 and 9. So chapter 22. Let's find it. Okay. So what's your question on number 8?
For number 8, I was mostly confused on finding p hat, z, and the p-value.
So a husband and wife, Stan and Lucretia, share a digital music player that has a feature that randomly selects which song to play. A total of 2,643 songs have been uploaded into the player, some by Stan and the rest by Lucretia. They are interested in determining whether they have loaded different proportions of songs into the player. Suppose that when the player was in the random selection mode, 27 of the 40 songs selected were songs by Lucretia. Let P denote the proportion of songs that were loaded by Lucretia. Okay, a lot of talking. So what do we think the null and alternative hypothesis is here?
I had D. Yeah, I don't know if it's the same. P equals 0.5 versus P does not equal 0.5.
Yeah, because we want to see if they're the same versus not being the same, right? Okay.
Yeah.
Okay. So how strong is the evidence that Stan and Lucretia have loaded different proportions of songs into the player? Make sure to check the conditions for the use of this test. So, I mean, these, of course, already give us the answers here, but let's see what it says. We expect, yeah, I mean, if it's really 0.5, then we expect 20 successes and 20 failures, right?
Okay. Yeah. For that part, I had put 0.5 and 0.5, so that's probably.
No, it's not. We don't put
half and half.
Right. We don't put 0.5 successes and 0.5 failures, but half of the sample to be successes, half of the sample to be failures, right? Which are both at least 10. Okay. And because they're both 10, then we can use the large sample Z test, right? The conditions for the large sample Z test are satisfied. Okay. So we need our p hat. P hat is 27 over 40. Right, which ends up being, I guess, 0.6750.
Yes.
And then we need our T statistic. What is our T statistic going to be?
That's the part I'm confused about. Oh, T.
Well, we have a formula for it, don't we? It should be p hat minus 0, because that's the null hypothesis. No, sorry, it's p hat minus 0.5, because the null hypothesis is 0.5.
Okay.
Over the square root of 0.5, 1 minus 0.5 over n, right?
Yes.
And if you just do the math on that, that should give you, 2.2136.
Okay. And the formula you said one more time, so I can just write it down.
The formula was p hat minus p naught. So p hat in our case minus 0.5 because we're assuming it's 0.5. P hat minus 0.5 over the square root of 0.5, 1 minus 0.5 over n being 40 in this case.
Okay. I got that one.
Does that make sense? And then we want the p-value.
Yes, it
How do
does.
we find the p-value once we have z?
Can we just like look on the table that we have?
Sure. Or you can use a calculator, or you can use crunch it. There's more than one method, but in all cases, you get 0.0269.
Okay.
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 Now that's a very small p-value.
Yeah.
Less than 0.5, less than 0.05, less than 5%, which means chances are we're going to reject the null hypothesis, right?
Yeah. Yes.
So there's strong evidence that it differs than 0.5.
Yes.
Are the conditions for the use of the large sample confidence interval met? If so, estimate with 95% confidence the proportion of songs that were sold by Lucretia. So even though we expect 10 of each, we didn't quite get 10 of each, right?
Yeah.
We actually did get 13 of one and 5 of the other, correct?
Yes.
And 13 of one and 5 of the other is not quite enough to do the large scale, the large sample size t-test.
Yeah.
Okay, because we need 15. Okay, does that make sense?
Yeah. Yes, it does.
Okay, well that's that one.
Yes, thank you.
You're welcome. Another question, or is that it?
I just had number 9, just how to find the A and B for the confidence interval.
All right.
I got the rest of that question, but
All right, let's take a look at number 9. It says, which type of fast food chain fills orders most accurately at the drive-through windows? The quick service restaurant, QSR magazine, drive-through study visitor. Okay, whatever, all this kind of stuff. So at the end of the day, we got 42 of 457 orders were screwed up, right? That's at the end of the day, the math that matters here.
Yeah.
What proportion are filled accurately? So we got to flip it. It's going to be 412, right? Okay, so let P denote the proportion of all orders that are filled accurately. That's the actual value that we do not know.
Yes.
We want to construct, as it says here, a 95% confidence interval for P. So are the conditions for the appropriate statistical procedures met? Yes, there's 42 failures, there's 400 something successes, there are at least 15, we're good to go.
Yes.
Okay, so then we want to determine a 95% confidence interval. Now, if I use crunch it here, it'll of course just give me A and B. But what if I don't have crunch it? What if I'm on a desert island and I don't have crunch it? What do I do in that case? What do I do if I don't have crunch it?
You can use the formula.
You can use a formula, which is P hat, my actual sample value, plus or minus Z star square root of P hat 1 minus P hat all over N.
Yes.
And when I plug that in, it's going to give me something plus or minus something else, right?
Yes.
So the minus something else, that gives me the left edge. That gives me the A. Plus something else, that gives me the right edge. That gives me the B.
So we couldn't, like, where it says P hat plus or minus Z star, or Z times, we couldn't just like you put the minus and then solve the equation and then put the plus and then solve it like that.
Of course, that's perfectly fine.
Because I did that like a couple of times and like it said it was wrong, and that's why like it gave me the equation. I put it in that.
If you did the math wrong, you could have been wrong. But if you do it that way, that is the correct way of doing it. That much I can tell you.
Okay. So I was probably just doing the math wrong.
That could very well be. but that certainly is the correct method.
Yeah.
And then in this case, because what are we looking for, right? Right, so we're 95% confident, 95% confidence.
Yeah.
95% confidence that
Mhm.
between, okay, so A is 0.88, that's 88%. So 100, so 88.15% and 93.45%, somewhere between those two numbers will be the numbers where it's accurate.
Yeah.
Make sense?
Yes, it does. Wait, and you said we can use a crunch it to find A and B also?
Well, yeah, I guess you could put in the number of successes, the number of trials, and the confidence, and it'll probably give you everything you need.
Okay.
All right, go ahead and load it up. See if that works. Sound good?
Yes. It would be under statistics, and then what do we hit after that?
Under statistics, under confidence. Oh no, confidence will come later. Under proportion,
Okay.
and it would
One
be
sample?
a one sample proportion.
Oh, okay. Found it.
Right, a one sample proportion.
And for the successes, we would have to flip it. We do 457 minus 42, right?
That's right. That will be the number of successes. That's correct. That is correct.
Okay, yes, it works.
Make sense?
Yes, it does. Thank you.
Okay. I'm gonna stop sharing and pause.